Continuing with section 1.3 on complex numbers, we want to look at example 2, where we simplify using imaginary numbers. So part A says to simplify the square root of negative 49. Previously we said that's not a real number. That's true, it's not a real number, but it is a complex number. So how would we do that? Well, let's break it down to 49 times the square times negative 1, right? So now we know our square root properties say we can take the square root of 49 and get 7, and we can take the square root of negative 1, and what do we get? I. The square root of negative 1, remember that's our definition, the square root of negative 1 is equal to I. Anytime we see the square root of negative 1, we simplify it to I. Okay, let's try that here. We've got 27, negative 27, right? 27 is not a perfect square, but it has a perfect square factor. It has a 9. 9 times 3 is 27, and then we have our negative 1. Square root of 9 is 3. The square root of 3, that's going to have to stay under the radical. The square root of negative 1 is I, and so there we have it. 3I square root of 3. Now, you could put the I on the end, but the problem is sometimes it's hard to tell if your square root bar is going over it. It could get marked wrong. It's better to put it in front, then you know it is definitely not under the radical. That's not what you intended, because that would be wrong to have it under the radical. All right, and then 125, let's look at that one. The perfect square here would be 5, because 25. 5 times 25 is 125. That's our perfect square factor of 125, and then negative 1. So here we get what? 5. The square root of 5 will stay. I square root of 5. Okay? So imagine these being a b squared minus 4ac. You're working out a quadratic equation. This is your discriminant, negative 125. So you would continue to simplify. We can do operations with complex numbers. In this case, we want to learn how to add and subtract complex numbers. Now, this is pretty much intuitive. I bet you could do it without me even showing you what to do. We want our answer to be in standard form, a plus bi, but I bet you know how to do that without me even showing you. We want to get the real parts together, 4 plus 6, and the non-real parts together, negative 7i plus 3i, and we're done. It's that simple, right? For addition, everything on this side was positive. I just got the real parts together. You could take the step to put 4 plus 6 plus negative 7i plus 3i if you like to get to that result, but I don't think you need it. All right, here, subtraction is always a little bit trickier. So I am going to take a moment to distribute my negative because I don't want to forget that the 6i is negative, not positive. Okay, now we could put our real parts together and our non-real parts together to get 3 minus 15i. Remember, I is a number. It's not a variable. I is the square root of negative 1, right? So this is a number. It is a non-real number, a complex number that's non-real. Okay? All right, multiplying. Again, I bet you know what to do already, but let's just go through it. We'll distribute. 9i times 4, what do you think that is? Yep, 36i. You were right. 9i times 5i. Well, 9 times 5 is 45, and I times I is I squared. Okay, whenever we see an I squared, that's negative 1. We cannot leave I squared in any answer. That'll always be wrong. So let's come back through here and replace I squared with negative 1. That makes that negative 45, but that's not in a plus bi form. That's bi plus a form. So I've got to write that as negative 45 plus 36i. Now it's in standard form. All right, and here's another multiplication problem. What do you want? What do you just want to do when you see that? You want a FOIL, and you would be absolutely correct. 6 times 5 is 30. I times 6, 6i. Negative 2i times 5, negative 10i. Negative 2i times I, negative 2i squared. So now we know what we need to do. Combine like terms, replace this with -1, simplify, and get it in standard form. Okay, 30 minus 4i minus 2 times -1. 30 minus 4i, that makes this positive 2. And now get the real parts together and put them in front. A plus bi. Okay, very simple. Before we get to division, we need to understand something about a word called conjugates. If a plus bi is a complex number, then its conjugate is a minus bi. The product of a complex number and its conjugate is a non-negative real number. So if we multiply a plus bi times a minus bi, let's see what we get. First times first, a squared. Outside times outside, negative abi. Inside times inside, positive abi. Last times last, it's a positive times a negative, so it's negative b squared, I squared, right? bi times bi. Let's simplify. Of course, the middle terms cancel. We get a squared minus b squared, and I squared is never left in an answer. We replace it with -1, so that makes this a squared plus b squared, and look, there's no imaginary unit left. The answer is a real number, not a non-real number. So this is the technique. We're going to use this idea for division of complex numbers. Okay, so before we do that, we're going to do one last multiplication, but we want to multiply 6 minus 9i times its conjugate, which would be what? 6 plus 9i. So let's do the same thing, but now with a real problem and see what happens. First times first, 6 times 6 is 36. Outside times outside, 9 times 6 is 54i. Inside times inside, negative 54i. Last times last will be negative 81i squared. Okay, so 36, those cancel, minus 81, replace the I squared with -1, so we get 36 plus 81, and look at this, we get this nice real number. What, 117, is that right? 7, yep, okay, so that's how we're going to use that technique when we do division of complex numbers.